Hello friends. So in last video we have completed uh, Gauss's law and differential form and the special cases of Gauss's law. So now today we will discuss application of Gauss's law. Okay. So uh, uh, basically Gauss's law is applicable for any shape, but however there are geometry. So there are three geometry for which we can truly useful. It is truly useful for the calculation of electric field as well as electric flux. Okay. So application of Gauss's law. Although Gauss's law is always true, it is only a useful tool to calculate the electric field if the distribution is symmetric. Charge distribution is symmetric. Okay, so Gauss's law is useful in any way, but for calculation of electric field, we can use it when the distribution of charge is symmetric. So, number one, if the charge distribution spherically symmetry, then Gauss's law can be used with the concentric sphere as Gaussian surface. So, when the charge distribution is on a spherical surface on the sphere, then we can use spherical symmetry, and by using spherical symmetry we can find out the electric field using Gauss's law. The second one is if the charge distribution has cylindrical symmetry, then Gauss's law can be used with coaxial cylinders as Gaussian surface. So when the charge distribution is cylindrical symmetric, charge distribution જે છે એ સિલિન્ડર પર હોય તો એ કેસમાં આપણે કોએક્સિયલ સિલિન્ડર જે છે એને આપણે ગોસિસ સરફેસ તરીકે યુઝ કરી અને ગોસિસ લોનો યુઝ કરી અને આપણે ઇલેક્ટ્રિક ફિલ્ડ ફાઇન્ડ આઉટ કરી શકીએ. And number three, if the charge distribution has plane symmetry, then Gauss's law can be used with a pillboxes as Gaussian surfaces. So in this case, when the charge distributed over a plane symmetry over a plane, then we use Gaussian pillbox as a Gaussian surface, and by using this Gaussian pillbox, we can find out the electric field using Gauss's law. So these are the applications of Gauss's law. Mainly three symmetry by which we can use using this symmetry we can find out the electric field, namely spherical symmetry, cylindrical symmetry, and space plane symmetry. Okay. So now next is fill around an infinite line of charge. So in this case, we have to find out the electric field as well as electric flux uh, due to this line of charge, infinite line of charge. So consider a uniformly charged wire of infinite length having a constant linear charge density lambda. Charge density means charge per unit length. Okay, so from figure 11 we can see that there is a infinite length wire having charge which is uniformly distributed. Okay, and so the charge density, that is linear charge density, and that is one dimensional. It is denoted as lambda. So charge density is nothing but the charge per unit length. So now let P be the at a distance r from wire, and E be the electric field at point P. Okay, so now from this infinite line charge or infinite line length wire, at distance as there is a point P, and at that point the electric field is E. The distance from line to point P is R. So now a cylinder of length L, radius R, closed at each end by plane caps normal to the axis is chosen as Gaussian surface. Okay, so now to calculate electric field we have to choose Gaussian surface, and for this case we have choose cylinder as a Gaussian surface, cylinder of length L and radius R, which is closed at both the ends and normal to the axis of the Gaussian surface, chosen as a Gaussian surface. So we have here considered the cylindrical symmetry of length L and radius R. Okay. So now by symmetry, the magnitude of electric field will be the same at all points on the curved surface, the cylinder and directed N cap radially outward. Okay, so the cylinder, which is having the radius r and length L. So on the surface, curved surface of the cylinder, the electric field on all the point on the curved surface will be same. દરેક જગ્યાએ કર્વડ સરફેસ પરના દરેક પોઈન્ટે ઇલેક્ટ્રિક ફિલ્ડ જે છે એ ઇલેક્ટ્રિક ફિલ્ડ કેવું હશે, સરખું હશે. ઓકે, કારણ કે ઇલેક્ટ્રિક ફિલ્ડનો સોર્સ એટલે કે લાઇન ચાર્જથી કર્વડ પરના દરેક પોઈન્ટ જે છે એનું ડિસ્ટન્સ જે છે એ સરખું છે, તો ઇલેક્ટ્રિક ફિલ્ડ પણ કેવું હશે, સરખું. ઓકે, and yes, electric field and the area that we have considered both are in same direction. Okay, on the curved surface we have considered small area, so the direction of the small area and the direction of electric field both are same. So area vector n cap, which is radially outward, and the electric field E, dot product of E and N. So E dot N is equals to E, because both are in the same direction, therefore the angle between them theta is equals to 0, and so therefore E dot N is equals to E cos theta, where cos theta, cos 0 and cos 0 is 1, so therefore its value is E. So now from Gauss's law, uh, we apply the equation of Gauss's law, that is integration over surface S E dot n cap into dA. Here n cap is the area vector, E is the electric field, dA is the area we that we choose. So E dot n cap into dA, that is equals to closed loop integration E dot dA, because as we know that E dot n is equals to E, so therefore E dot dA, and that is equals to, according to Gauss's law, Q enclosed upon epsilon 0. So now E is constant everywhere on the surface of the cylinder, so therefore E is outside the integration, so E into integration dA. So integration dA, that is the cylinder. So for cylinder the area is 2 pi r L. Cylinder no area જે શું થશે 2 pi r L. So integration dA is equals to 2 pi r L. So E into 2 pi r L is equals to right hand side Q enclosed upon epsilon 0. Okay. So now instead of Q enclosed, we can write lambda into L, where lambda is the linear charge density and L is the length of the cylinder. So if we substitute the value of Q enclosed, then we can get the equation E into 2 pi r L is equals to lambda into L and upon epsilon 0. Okay, and now we make subject E electric field. We want to find out electric field E, so therefore we make subject E. So E is equals to lambda upon 2 pi epsilon 0 into R. Here in this step, length on the left hand side and length on the right hand side both are the length of the cylinder, therefore it gets cancelled out, and the remaining term on the left hand side, that is 2 pi r, which is on the right hand side, it will at the denominator. So E is equals to lambda is equals to lambda upon 2 pi epsilon 0 r. So this is the equation number 18. Now we have studied the case of the area which is on the curved surface. Now for both the end, upper and lower end, if we consider area as shown in figure, at the upper and lower end, if we consider area, that is dA, so the direction of area, that is dA, pointed along the direction of the length of the wire, and at the lower end again the direction of area is along the direction of the length of the wire. So both the electric field, direction of electric field, and the area which we consider at the both the end are perpendicular. So in this case, E dot n, electric field and the area vector n both are perpendicular, so E dot n becomes 0, because the in this case angle is 90 degree and cos 90 is 0. Okay, so for both the sides of the cylinder, E is perpendicular to dA, therefore E dot dA is equals to 0. And for the case of the electric field which is on the curved surface, it falls like 1 upon r. This is we can say from equation number 18, because in equation 18 Lambda is the line charge density, which is constant. 2 pi is constant, 2 constant, pi constant, epsilon naught, free space permittivity is also constant. So here R is we can vary. So if we vary increase R, then the electric field is decreases. If we decrease R, then electric field is increases. So the electric field of the infinite line is falls like 1 upon R. Okay, thank you.